Thank you. So I'm Jean-Luc. I work for Intel as a microprocessor architect, but before that, I was doing film animation. I've done games, and now I'm doing graphics and hardware, which is surprisingly similar when doing it in software. I'm also associated with the University of Victoria. I'm a PhD student. And I'm going to talk about texturing. Texturing is something that's very intuitive. We all understand what texturing is. This is programmer art. In fact, it's double programmer art because I generated the texture by writing code. That bee is the mascot for a processor project we had called Larry. And so it was Larry the Bee, which was, what was his interest? Larry the Bee was our mascot. And so texturing is a very simple process of applying an image and decaling it onto geometry. And so intuitively we'll understand how this works. But there is a lot that goes on in the hardware and into making this efficient. And so I wanted to talk a little bit about what the hardware does, how it does its thing, and what tricks it plays to make this very fast. And I guess the idea behind this is to try to figure out how to understand the hardware as best as possible. So I'll go over a little bit of the details of texturing. I'll talk about how it's implemented in the hardware. So the texture sampler, it's a fixed function hardware block, which does just texture. And it needs to perform the address computation for the texels that you're trying to read from memory. It needs to hide the latency of the memory accesses, which can be quite slow. Sustain throughput and output a single color for the request. And all of this needs to happen asynchronously. So this is what the hardware is designed to do. And so here's a bit of HL cell code where we set up there's a texture that's going to be bound somehow in the pipeline. Set up a sampler and we set up some state in the sampler. We're going to use MIT mapping. We're going to wrap the U and V's coordinate. And we have a bit of an input and output defined for the pixel shader, and the pixel shader just does a texture lookup. So this is what it looks like in the code. And so the question is, well, what happens beyond this? And so we have the HL cell shader, which is going to be fed by the application to the driver. I'm mostly talking DX, but OpenGL is exactly the same. This driver is going to feed the shader to a compiler, and then this is all going to be sent down the graphics pipeline to the GPU, and the GPU will eventually run the shader, which will call into the texture samplers. And so we understand very well what happens up to the application. This is what we're used to working with. I will not really talk about the driver, the compiler itself, but I'll talk about what happens beyond there. And all this information is available. It can be found. It's a little bit difficult to track it down. None of it is all in one place. And it took me a long time to get all the pieces of this picture. So we have a pixel on screen which maps to a region of the texture. Often it's a region that covers multiple pixels. And this pixel has a set of UV coordinates. And so let's say that the triangle setup code or hardware generated UV coordinates, 0.45 and 0.36, and we have a texture that's 256 by 256. If we multiply the two together, we get an address, and that address is 57.6 and 46.08, and that corresponds to a point inside a pixel. And of course, if we're using simple bilinear filtering, we have to blend the 4 pixels in this region into one color. And so the way this happens is we do linear interpolation. So we take the fractional part, which is 0.6, and so we're 40% of one pixel, 60% of the other pixel is mixed together. We do the same for the bottom row, and finally we linearly interpolate those 2 colors into a final color, and this is what it looks like. Now, when objects are far from the camera, things get complicated because your one on-screen pixel covers a larger area in the texture. And so what we have to do is somehow average all these pixels that are covered into a single color. So this is texture minification, and I'll show you a little bit of the details of how this is done. Essentially what we do is we pre-filter our texture by computing versions of this image at half the size. And every time we compute half the size, and we get a pyramid of images. And then the trick is to figure out which image should we read from in order to get a good approximation. And so this process is essentially, so the filtering is like a low pass filter, and we want to sample at the right frequency in order to avoid high frequency spikes. And so the math is a bit scary, but it's actually very easy to understand intuitively. You have a pixel that is distorted in texture space, and what we do is we measure the 2 edges. So off over. So we're measuring these 2 edges, and in this example, the 2 edges are approximately the same length, so it's isotropic. And so we're computing the length of the hypotenuse of those 2 triangles, and so essentially we're looking at the partial derivatives of the pixel and the texture space of the texture, and we're computing the length of these 2 hypotenuses and picking the largest one. And the log of that number is going to be the level that we're going to look at. So if I guess this is a good place to look at anisotropic sampling. This triangle is going to be a lot higher, a lot wider. And so the best way to handle that is to just take multiple samples. I'm not going to go over the math for that, but it's very similar. And I guess I'll just point out that these derivatives are computed by code that's generated by shader compiler during triangle setup. And these are fed to, these can be fed to your shader program and certainly to the process that computes the LOD. So we get a real number out of this process, and we just take the upper and lower integers as the 2 levels that we're going to sample, and we get 2 colors out of that process, and these 2 colors are then linearly interpolated. So this gives us trilinear filtering. There's 3 levels of blend. And so in this case, we've had to look at 8 pixels in textures in order to come up with a single color. So we're going to memory 8 times. There are 8 memory probes. So how do we go to memory? We have to compute the address for each of the pixels that we're trying to look at. And this process is a little complex, but it's very fascinating in a lot of ways. So I'll show some of the details. The surface type plays into it, surface format, the wrapping mode, and the surface squizzling mode. And so we'll go over the details of these. But some of them are fairly intuitive. So surface type, we have a 2D texture, we have a 2D with a series of mid-levels, 3D textures, which is just a bunch of 2D slices. An array is just what you think it is, it's an array of images. Cube map is 6 images arranged in this specific fashion. But there are other, it gets complicated from there. So you could certainly have an array of cube maps, and each face in the cube map is mid-map. And so the layout gets quite complicated, but we'll stick with the simple cases. So the surface format is what data is contained in the texture. We can have RGBA textures, which is what we're used to. This second one is interesting. It's a packed YUV format, so you have the data is separated into the luminance and the chrominance channels, and the Y here is you have one luminance value for each pixel, and you have shared chrominance value for both pixels. So you need to read 32 bits of data to get the full information, but out of that you get 2 pixels. DXT5 is a compressed format that will contain a group of 4x4 pixels and 128 bits, which is 8 bits per pixel on average. There are various floating point formats, so this one will store 2 float 11s and then 1 float 10. And the last format is a 16-bit format, which stores, 5 bits, 5 bits, 5 bits, and 1 bit alpha. The important point out of this slide is that different texture formats have different take a different number of bits, and so we need to know that when we go from one pixel to the next in memory to figure out how far apart they are. So border mode, that's also fairly easy to understand. We have clamp, where the last row of pixel at the edge of the texture is repeated forever after. So if your texture coordinates go beyond 0 to 1, you will get the last pixel repeated. Wrapping, it will start repeating, so this is 0 to 1, this is 1 to 2, and goes on. Mirror is the same, except that flip the image. Border color is interesting for testing often. It allows you to specify a color to use if you go out of the range of your texture, and so it's fairly easy to detect visually that something has gone wrong. So linear addressing, we have essentially an array of pixels in memory, it's like a 2D array, and so we need to compute the address of any one of the pixels in this texture. So we have a base address, which is the address of the top left pixel. We have the x and y, which is the address, the coordinates of the pixel we're trying to access, and width is the width of the image. So it's pretty easy to see how to address into this. Of course, you have to remember to multiply by the size of each pixel. So you need, if pixel takes 4 bytes, then you have to advance in steps 4. And so let's look at a common and easy to think about example. Let's have a 4-channel image that has an R, G, B, and A channels. 8 bits each, so a total of 32 bits for each pixel. The texture has a nice power of 2 size, 256 pixels by 256. In binary, by 1 to go from the red to the green channel, and then we added 1 again. We moved by 1 byte to go to the blue channel, and we moved by another byte to go to the alpha channel. And so, if you look at the bit pattern in our address, you can see that these last 2 bits specify the channel that we're trying to access in the texture. So far, so good. So, if we look at the top right pixel, it's the 256 pixel in the first line, and we can see that there are 8 1-bits in this address which we've computed. And so to visualize this, I've just identified all these bits as X's. And so we can see now that we have a bit more understanding of how this address is computed. And then if we add, if we look at the bottom left pixel, and we look at the bits that got set when trying to access this pixel, we have a complete understanding of what the various bits in our address do. So, of course, memory is accessed in units of cache lines, and so if we use 4-byte pixels and we have a 16-byte cache line, we have essentially a linear array of 4 pixels. If we use a longer cache line, then we get more pixels. And this is actually, this is not very useful because triangles are not long and linear, but they cover a certain area of screen. And so if you have very long cache lines, you're going to cover a lot of triangles, and you're better to have cache lines that are that cover a rectangular tile of a screen. And so this is where swizzling comes in. And so Morton order is this nice pattern, Z-shaped pattern, where you access pixels. So if we go from the first to the second, we move right, then to go to the third, we're going to move down the left, and this is our fourth. And this pattern is nicely recursive, so as we go to a larger tile size, we're going to go in this Z pattern again, and so on, and so forth. And Morton order is very interesting because in order to implement this, you'll find that the bits of the X and Y coordinate of the pixel are interleaved. And so this is not really obvious, so what I've done is I've just looked at the first 4 bits, and this is a simple counter in binary, and so as we add 1, we're just counting in binary. And if you take then the 2 X's and the 2 Y's and organize them like this, you will see that as this counter increases, the pixels that you traverse on the screen are in this nice Morton part of the pattern. So the interesting thing about this is that in software, if you try to write code that takes 2 8-bit numbers and tries to interleave them like this, it's quite tricky. There are no easy instructions to do this kind of bit manipulation. In hardware, it's very easy because you're just crossing wires. And so, for the hardware guys, this is not an issue at all. But if we try to implement this in software, it gets quite slow. So with this Morton access pattern, our cache lines are now going to be these nicely square shapes. This is assuming, of course, 32-bit pixels. So we get 4 pixels in the 16-byte cache lines, and they're going to be accessed in this Z shape. We have a larger file, then we're going to access all of these pixels in this order. But now, this is interesting because if we have a triangle, and our triangle covers, say, this part of the texture, one cache line will contain all the textures, all the texels that we're trying to sample. Tiling. So there's an additional twist to addressing, which is that it often is useful to access data in tiles. And so if we have a tile that's W by H, it may be a DXT block, so it's a 4x4 blocks of pixels, or it may be a full memory page. So our 32-bit pixels will, you will fit 32 by 32 in the memory page. And it's whatever works for the hardware. So tiled addressing is not very hard, but it takes about a slide to implement. So if you have an image of size W by H and a tile of size W by H, so we compute the size of our image in tile. And so this is rounding up essentially the size of our image to the next integer number of tiles, and then we take an address xy, and if we divide it by the size of the tile, we get the address of the tile that we're looking for. If we use the modulo operation, then we get the address in the tile. And so this is the computation that we have to do in software to figure out which tile and which pixel to access. Well, if we look at the bit pattern for this thing, we'll notice that these sets of bits are actually the address inside the tile, and the rest of the bits address the tile itself. And so in this example, and it may be a little bit hard to see the indices here, but we have x0, y0, x1, y1. So this is the address inside the tile. It's a 2 by 2 tile, and it's in Morton order. And then we have those bits that contain x2 to x7 and y2 to y7. And so those are the tiles arranged in linear order. So for the hardware, it makes no difference whether we're using tiling or not. It's just a matter of rearranging the wires. In software, it took a page of code to actually figure out how to address. So I'm not going to talk about MIP layouts, cube layouts, array, 3Ds, padding requirements. All of this stuff needs to be specified by the hardware, but in a sense, the driver does this for us. And so we don't really need to worry about it. But those details do happen. So now that we know the address that we're trying to access, we can do a memory fetch. And the problem with going to memory is that it's very, very slow. So it can take on the order of 1,000 cycles. And if you have to wait during 1,000 cycles to get the data in order to proceed, it's just horrendously slow. So what we do is we try to interleave, we try to have the GPU do something while this memory fetch is in progress. And when we do the access, we'll get one entire cache line, whatever its size may be. It'll be somewhere between 16 and 64 bytes. And so and we also know that each sampling request that we wrote in our HLSL code results in multiple memory probes. So the trilinear filtering we looked at will generate 8 probes. We're using an anisotropic filtering mode, and it needs to do 16 taps in order to filter a highly distorted pixel. That will, each of these taps results in 8 probes. So we have a total of, so this one pixel you're trying to cover will access 128 different addresses in memory. And so it can be quite expensive. Now the sampler will try to have thousands of requests and flights in order to hide this latency. And as soon as a fetch is issued, it will go and move on to the next texture request. In some instrumentation I did, I found that on average, DX9 games tend to do one texture read about every 50 shader instructions. And in shader instructions, I'll also include triangle setup, so it's maybe a little more instructions than you actually see when you disassemble your shaders. DX10, DX11 will probably do more. You're running more complex shaders. You're probably going to do more texture accesses. And another interesting thing I found is that the average triangle size is about 10 pixels. So a triangle will cover, say, a grid of 3 by 3 pixels. And so this means that for each cache line you can expect to get 10 cache hits. And of course, if your cache lines are square, then that's much better. In hardware, we get over 95% hit rates in the texture caches. And so the interesting thing is, because those triangles are very small and access very small areas that are nicely organized in cache lines, the data doesn't need to stay very long in the cache. After about 10 pixels, you're done. And so texture caches are designed quite differently from CPU caches. So precision. This is something that's interesting, and I didn't used to think about that at all. But there are a bunch of precision issues in the DX pipeline. So we have texture coordinates that are represented by floating point numbers in the range 0 to 1. And IEEE 754 specifies the layout for bits in the floating point number. And you have essentially one sign bit, you have an 8-bit exponent, and a 23-bit mantissa. So the exponent is applied to the mantissa. It's essentially the scale of the number. And so the way to think about this is mostly have to do with wrapping. If you're gonna have a range of UVs that's bigger than 0 to 1, then this is where the bits go. They'll all go into the exponent. So the mantissa is what specifies, what allows us to address individual pixels in our texture. And we have 23 bits of mantissa. So both DirectX and OpenGL require 6 bits of fractional precision inside a texel when we do the computations. So if you subtract those 6 bits, we're left with 17 bits to address individual texel, which puts the limit to 128,000 pixels. So you can have the maximum the largest texture you can have is 128K by 128K pixels. If you go beyond that, your floating point UVs will just not be able to address every pixel. They're going to skip. Now DX limits the texture size much lower than that. You have DX10 is 8K in any dimension. DX11 is 16K. I'm not sure about DX9. It's either 4K or 8K. I believe it's 8K. But this is the maximum texture size that is supported for direct access. So when you take your UV coordinates and you scale that by your texture size, and this is converted to a 16.8 fixed point format, and it doesn't really matter, the details don't matter, but the important part is that we have only 8 bits to the fractional part, which means that when we compute weights and we filter those colors together, there's only a range of 255 positions between two values, between 2 pixels, 2 pixels. And similarly, the LOD has an 8-bit fractional part as well. This is not too important in graphics. It is visible in some instances, but this turns out to be very important for people trying to do work on GPUs using CUDA and OpenCL, where if you're trying to use your texture sampler to do some filtering asynchronously, you have a big issue of the precision of the results. So large textures can be handled in several ways. John Carmack has been using mega texturing for a while on terrain. Sean Barrett has a technique called sparse virtual textures, which is quite nice and uses dependent texture reads in order to simulate virtual memory, so that's a bit slow. And I've been working on a technique called demand page texturing, which requires hardware support. But that's not really what I want to talk about. So I want to finish figuring out what goes on in this texturing process. And so the data in the texture is in some format that is specified at the time of sampling. So the various options there are unorm, where you get an integer value that represents a number in the range 0 to 1. If it's signed, then it's in the range -1 to 1. You have regular unsigned ints and signed integers. Some textures you can tag as sRGB, which means that every time you read from the texture, it is the gamma correction is automatically undone, so you can blend in linear space. And if you use a render target, then when you write to it, it will automatically be converted back to sRGB. And then there are various floating point formats that can be used. And so we've got 10-bit, 11-bit, 16-bit, 32-bit, 64. The 32-bit floating point format on GPU is essentially the same as the float format on CPUs, with minor differences that are that have to do with the handling of denormalized numbers, but that's pretty geeky, and there is really no point in talking about it in the context of graphics. And there is a shared exponent format where you can have RG and D share a single exponent, and this is useful for HDR. So this is the data that is in the texture. And so this is the slide we were looking at earlier, and it should now make more sense what these suffixes mean on the format names. And finally, so you get this data out of memory, and you have to hand it back to the shader program. And this is very dependent on the format that you pick. So here I have 5 examples. The first one is good old RGBA that we've all learned to love, where the 4 channels that we read end up in the 4 channels that our pixel shader gets. Now, if you specify that your format is RGBX, then you get a 1.0 value for alpha, no matter what was in the texture. The texture is not going to be read. This I32 float format essentially means that you have in your source texture a 32-bit floating point number. And in this case, it will show up, the same number will show up in all 4 channels of your shader. But L32 essentially has the same data in memory, but it will have 3 channels contain the value, and the other channel will contain 1.0. And alpha does the opposite. You get 3 channels that contain 0, and the last channel will contain the value that was in the texture. So this is quite easy to do in hardware, but if you're trying to implement this in software, it's quite messy, because you have to handle all these different cases where the data is mixed in various different ways. So why is this hard? Well, writing code to implement this whole pipeline that I've described in a few slides is not that hard. It's not that much code. And I've done it in 2 or 3 pages of 2 or 3 screenfuls of code. And if we want to be really smart, we may want to, based on the on the state of the sampler that's being passed, we may want to JIT the shader code, the sampler code. But it turns out that there are a lot of details that are tricky to handle. So when you're sampling from a cube map, you may cross between one face and the next, or you may have to sample right at the corner. When you're filtering, we looked at filtering, and it was all nice and easy because you were looking at 2 by 2 pixels. But if you're right at the edge of the texture, you don't have 2 by 2 pixels. So what do? You have to replicate the last pixel and use that. You have to handle all the specifics of address generation when you're going outside the range 0 to 1. And all of this stuff really needs to be tested and evaluated at runtime. And this is quite slow, and you have to do it on every single texture access. You can't just JIT that away and make it very efficient. And so the code ends up having lots of ifs and conditional branches, and all of that makes the code very inefficient. And so this is the big reason why, one of the big reasons why we use hardware to do this. Memory access, well, we've talked about how it might take 1,000 cycles to get data from memory. And so we need to hide the latency of these accesses and sustain throughput, which means we need to always issue a request and move on to the next piece of data so that we can keep busy while these 1,000 cycles of fetches are happening. And then when we're done, well, hopefully the data starts coming back. And this last item is we need to uniquify the cache lines. So we're going to access a lot of data that goes to a lot of places in memory, but by the time we're looking at the granularity of cache lines, hopefully a lot of that data will map to the same location. And so we don't want to trigger memory fetches if we've already triggered one where the data is all there. And so the problem is you have all these requests, and we've seen it can be 128, and you have to make sure that you only issue unique requests. And so all of this testing is tedious and slow. Latency hiding. Well, we can do this in software. I mean, it's just a matter of running enough threads and making context switching lightweight. But each thread has its associated storage, and if you're running hundreds of threads all shading, that's quite a bit of stuff to do in software. It needs to be fast, it needs to be non-blocking, so the code complexity is quite high. Now, every time we try to access a piece of memory, if it's not in the cache, it will go. The processor stalls, essentially. So you have to make sure you prefetch every piece of memory you're going to ever access. And if you miss that, then now you're blocked and waiting 1,000 cycles. So that's very difficult to do on the CPU, to do efficiently. And caching, so CPUs have read and write data. So if you need to read new data and put it in the cache, you're going to select the cache line, and you may have to write the data that it contains back to memory. So you want to select your cache line. If it needs writing, you issue the write request. Then you issue the read request, and by the time the write request has completed, the new data shows up, you replace the data, and you move on. In a GPU, most of our texture data is read-only. And so you don't, and it is short-lived. So you don't want to reserve a cache line for 1,000 cycles when you might not need it. And so what we do on a GPU is we issue the read request and don't allocate a cache line until the data shows up. For the most part, this is okay because by the time the data shows up, we should have plenty of old data in the cache that we can flush. Remember that each line of data is accessed on average 10 times. So these caches save a lot of bandwidth, but will not help hide the latency. So recommendations, given what the hardware does, how do we use it properly? These recommendations you've probably read about in a bunch of places. I'll try to illustrate some of them though. So do math in shaders. Shaders are very efficient. And so whenever you use textures to store tables of data, you're going to have to use a texture sampler to go get that data that has lots of latency. You could, instead, you could just compute the data on the fly. Sometimes you can do that for free because your shader cores are idle, waiting for this data to come from memory. And so it might, well, increase your performance to not use textures in some cases and just do extra math. And this is a little bit counterintuitive, but it's surprising. It works surprisingly well. Avoiding dependent reads. So dependent reads are when you read a texel from a texture and use the values that you read in order to go and get another piece of data from a different texture. And so the problem is that you have a dependency chain and you cannot optimize this way, because you can't figure out where you're going to read the second texel until you've read the first one. Compressed textures, that's pretty obvious. You want to save the bandwidth there. The problem is that it's really hard to know when you can get away with compressing textures. Very often it'll look good enough in most cases, and sometimes it's not good enough. It's really hard to track down. And data that is not image data is even more difficult to deal with. Although in DX11 there are BC6 and BC7 formats that can help. But in general, it's really tricky to do a good job at compressing the textures. And the best way is to compress it and then look at it, compare the compressed image with the original one and see the result. And my last point is you want to work really hard at only uploading data that is going to get used in the frame. So DX allows to do resource management at the granularity of a single link level, and this should really be used. It's often not. So I have a couple of examples. This is World in Conflict. This frame uploads 38 megabytes of compressed data. There is other uncompressed data, but I chose not to show it in this example because it would skew the results much more in the favor of what I'm trying to show. But even in this case, the compressed data, most of it is never looked at. So in drawing this picture, 73% of the texture memory was never sampled. And so it didn't need to be uploaded. So if we look, in fact, at how these textures are sampled, we see that, so this slide is a bit tricky to read, but let's see how this works. So in the 30% bucket, we see that all these textures, which is about 15% of the textures in the game, had less than 30% of their pages of memory looked at. Now, I did this at the granularity of 4K pages. If you look at this, at the granularity of a single cache line, this gets much worse. But at this level, GPUs will do the management most of the picture. And in fact, we have less than 5% of the textures in the frame are completely red. So this picture for me is quite interesting. It means that really most of the textures are accessed at have very, very small areas that are accessed in any single frame. So if you look at another game, Crisis, this is a frame that was in the intro sequence, and so it's quite easy to capture that data when the game runs automatically to do analysis. So this frame uploads 18 megabytes of compressed texture data and does not sample 64% of it. It does a lot more texture work. We've got a lot of bandwidth being used, but it's always to the same place in the same textures. So, well, okay, so you say, well, you're looking at a single frame, and when we play a game where we're looking at sequences of frames, and so maybe these areas move over time. So I did an analysis of world in conflict. So I'll show you a sequence of frames. And these frames are exponentially separated. So the first frame is this one. This is one frame later. And then this is 2 frames from the original one. This is 4 frames from the original one. I'm trying to see how this changes over time. And so you can see that this frame is now quite different and looking at quite a different data set than the original one. And as we move along and we have a big explosion, this is probably different effects that are being run. You'd expect completely different sets of textures. And by frame 256, we've had a camera cut and we're looking at something completely different in the game. So at the granularity of pages of memory, this is quite interesting. It shows that essentially from frame 0 to frame 1, we have brought in about 7.5% of new pages. And it doesn't increase that much over short periods of time, and even over longer periods of time, it holds quite well. So where we can advance the game by 64 frames and still have only shuffled 15% of our memory pages. So that means that really there's not that much data that is being looked at from one frame to the next. And so by being selective in with which MIP levels you upload to the GPU, you can get back quite a bit of memory. So that's what I have.
So the tech people should make questions now.
It is perhaps a naive question, but a big effort in accessing memory directly by the hardware to put textures on the screen for a fixed, let's say, a fixed image in memory. So isn't it possible to put the image in a different way in the memory so the access by the hardware is simpler?
So I guess I was trying to show that the Morton pattern is simpler for the hardware, yet it makes things more complicated for software. So it's really a trade-off between hardware and software. Well, some things will be easier in one framework or in the other.
It's a question of, let's say, drivers and putting the image in the memory.
Yeah, so the driver will hide the specific format that the hardware uses and tries to present a linear model to the user because it's easy to reason about it, and then we'll go on and swizzle data in order to make access to it more efficient, or maybe make the access patterns more cache friendly. Okay. I guess the other part of the answer to that question is that there is a question of power. So on a cell phone, device, you're very concerned with how much power you're consuming through this memory access. If you do everything in software, it's going to take a lot more instructions and a lot more power. If you do it in hardware, you can do this much more efficiently, usually.
I'm thinking more in situations that the texture is fixed. It's loaded once and it's never changed. So you can do it only once. The question is, take the texture image only.
Yeah, problem. But the texture is bigger than the cache, right? So there's always this question of streaming data.
Okay, I understand. Okay.
I have a question. If we're an artist and we have an artist creating a texture for the game, of course this will be transparent for the artist into doing the rendering of the game engine. But is there any occasion that the artist should take care of how to prepare the textures for the game?
I think as an artist, it's always nice to work with large images. So I always let the artist go crazy. If you want to work at 2K by 2K, fine. But eventually there's a point where we're going to reduce the image size and compress them so they fit in memory. And often, on game teams, like say big fights where people argue, oh, this should be 512 by 512. If we make it any smaller, it'll be horrible and we will notice. And you can usually go back in the pipeline, just change something in the code that nobody sees, and scale down the textures to 256 by 256, gain a lot of memory and people won't see it. So I think the truth is it's a compromise between tech people and the art people as to how much memory they can spare for textures. But definitely creating them, you should just use as much space as you want.
And in the case that maybe you have a 3D model that the artist creates a bunch of like 15 layers in order to create a specific effect, and you know that within map you can replace some of the layers. How?
But you can do it after the fact, right? You can flatten the image. I mean, a similar example in geometry. I was working on a golf game, and you know how a golf ball has all these little dimples. Well, I was in the game, and every time the golf ball would come into view, the game would call to a stop. And it took us a while to realize that we had 100,000 polygon golf balls. And it was just a matter of simplifying the geometry. And with textures, it's the same. I think there's a lot of value in working with higher res art and then down sampling it before it goes into runtime.
So let's thank Jean-Luc again, and thank you very much.